Welcome to Print Reading for Concrete. My name is Dan Dorfmiller, and I will be your instructor. This is Unit 6, Structural Systems and Drawings. First, let's talk about structural systems. Structural systems start with the foundation, which are typically below grade or at the grade portion of the structure. Elevated structure, which is typically above grade and structurally supported by columns, walls, and then the foundation. And then after we're done with that, we will review some structural drawings. So, let's get back to the foundations. The first would be a grade beam. It is it's trenched and earthen formed, and usually the use of very little other formwork will be needed at the top. And then the concrete is poured in it like that. Next would be a wall and footing, the footing providing the final earthen support. Another wall and footing type is a retaining wall. A retaining wall would be more complicated because it is not only carrying a downward load, it's also resisting a lateral load. The lateral load is caused by the difference in grade elevation. As you can see here, the grade's higher on this side than on that side, and is causing the wall to want to turn over that direction. So typically you will find the footing on the back side a little bit longer. Auger cast pile foundations are used when the loads are significant and the subgrade is poor, and the distance to good support is very, very deep. This would also be true for caissons, except the distance to good support is usually not as deep. Caissons are larger in diameter than auger cast piles. And the last one we will discuss in this training session is H steel piling. This system is typically used when both heavy loads and support is so deep it cannot be reached by excavation or drilling. H pilings are driven into the ground. Going back to footings and foundations. Foundations are the feet of the building, which the entire building rests. They are shown on foundation plans. The footing sizes are determined by the weight of the building, how the weight is distributed onto the footings, and how the subgrade is able to resist those forces. The grade beam is one of the simplest forms of building support. It is trenched into the earth, and the earth is used as temporary support while the concrete is placed into the trench. Wall footings are similar. They are also can be earthen formed or formed above grade. They are continuous and are the support under a concrete or masonry wall. Foundation walls are almost always somewhat below grade and carry continuous loads from the walls and the structure above the grade. They are used to transfer the loads down to the footings. The foundation plans are where the building support systems are shown. Here we can see wall footings, column footings, retaining walls that support the building above. Looking a little closer at the foundation plan and a detail, we see a section cut for detail 3 of a short wall and footing. Another example of a foundation plan with section cuts every time the wall changes detail. And to illustrate one of the sections cut in the foundation that is similar in several places, 4, 4A, and 4B. Also note there is a short concrete wall that supports a masonry wall as the building goes up. Column footings are for the column system within the building. The column loads are spread out evenly onto the subgrade support. Here we see an isometric and a sectional view of a typical column and footing. The column can be made of wood, steel, or concrete, depending on the load carrying requirements. Next is a plan view of a column footing with a concrete column, showing here the reinforcing steel, the column footing, and the column above. Column footings are almost always called out in a column footing schedule, as seen here and here. But the exception to the rule could be footings noted in a flag note on the foundation plan, as seen here. Here we have a column detail. Note the scale is much larger, so much more of the information about the column can be conveyed on how it is constructed. A retaining wall is a wall and footing that resists two types of loads. One is the building load from above, and the other is the earth overturning load. The earth overturning load is caused by a difference in earth elevations on one side versus the other. The inside portion of the footing is bigger to resist the forces that would want to push the wall over to the lower side of the earth. Auger cast piles are drilled into the ground with a very large drilling rig. The diameters are usually 12 to 24 inches and can be drilled very deep. I have seen them as deep as 100 feet. The loads are supported by friction from the subgrade or socketed into rock. As the drill auger is being removed, cement grout is pumped down the shaft to fill the cavity. A light amount of rebar is added to the upper third to assist in tying multiple shafts together into a pile cap. And looking on a plan, we can see what it would look like. Here is an auger cast pile cap, and here is the representative section. You see the pile cap, and you see the auger cast piles being tied into the pile cap, and you can see where these extra pieces of rebar are used to help tie that in with. Caissons are similar to auger cast piles, except larger and typically don't go as deep. They range in size from 18-inch to 72-inch in diameter. They also have steel reinforcement cages and pile caps. They will always be drilled into something solid, such as rock or substantial subbase material. When the bottom of the pile has been tested, the void is filled with concrete material. H-piling is for deep foundations where subgrades at the surface are marginal. The steel piles are driven into the ground until they hit suitable support strata or cannot be driven any further. They are cut off and grouped together into a pile cap. It is very common to see this type of work along beaches, riverbanks, and bridge overpasses. Slab on grade is a concrete placed on subbase material at the ground level, whether that be the basement or the first floor. The concrete slab can be without reinforcement, or when subjected to settling or heavy loads, it may be reinforced. Some slabs on grade are considered floating slabs, and they are structural, simply floating on the ground as one continuous unit. Most slab on grades, even though they have reinforcement, it is still considered a non-structural element. The reinforcement is to help resist cracking and assist in load-bearing capacity. Typical types of reinforcement are rebar, mesh, which is welded wire fabric, post-tension cables, and fibers, both synthetic and steel. The most common being mesh and rebar. Slab-on grades are typically shown on the foundation plan. Here we see two types of slabs. The slab on grade in the dock is without joints, while type 2 in the rack area has joints. The joints on this plan are indicated by dashed lines. A typical note specifying reinforcement in a slab might read, like for mesh, 5-inch thick slab with 6 by 6 W10 by W10 WWF over 4-inch ABC gravel subbase, or for rebar, number 4 at 18 inches on center each way over 4-inch ABC. The 6 by 6 is the spacing of the wire. The W10 by W10 is the gauge of the wire. And WWF stands for welded wire fabric. Almost all foundations will need to be waterproofed to eliminate the intrusion of water from below grade. Typically, there will be a barrier like tar and or more advanced systems, a layer of drainable gravel around the structure. Some concrete materials can include a hydrophobic admixture that protects the concrete from water intrusion. Okay, moving on to elevated structures. Most all commercial and industrial buildings are constructed with both reinforced concrete and structural steel. Looking at the building, let's identify some of the main components. Starting at the top, we have steel girder, then we have steel beams running here. We have a steel column. This would be considered an elevated deck. Here we have a concrete column, and here we have spandrel, soffits and spandrel beams. There are several kinds of concrete construction. Cast in place, which simply means cast on the construction site, which is most typical. Precast, which is cast off-site and trucked in and then set in place. And the two variations of this would be pre-tensioned and post-tensioned. Pre-tensioned, the cables are stressed prior to casting, and post-tensioned after casting, both adding compression to the concrete member and making it stronger. For cast-in-place structures, there are two basic types, one or two-way floor systems, or you might say flat plate and joist and beam. This can be a little hard to get your head around, but think about how floors are spanning across members, and this will help. Here we have a girder and beam system. The girder is spanning from column to column, and the concrete floor is spanning on the beams from girder to girder. This would be considered one way. Let's take a look at this parking garage where we have a girder beam running from column to column with a pan joist running from girder to girder. One-way floor system. A two-way system could look like this, where the floor is spanning both directions from column to column. Here is a physical example of a dome system spanning from girder to girder in both directions. Now let's take a look at reinforcing steel, better known as rebar. The authoritative resource is Concrete Reinforced Steel Institute, CRSI, and American Standards for Testing Materials, ASTM, neither of which we are going to review any further here. I encourage you to Google both and obtain more information. Rebar is designated in 1/8-inch intervals, starting with a number 3, which is a 3/8-inch bar, up to a number 18, a 2 1/4-inch bar. This chart gives the area, weight, and diameter for each bar designation. Rebar has markings on it designating its grade, 40, 50, or 60 KSI, and the mill that it came from, and the bar size designation. Rebar is used in all types of concrete structural systems. It is available in plain, non-deformed, or deformed. For structural concrete, deformed bars are most common. The deformations provide excellent bond strength between the concrete and the reinforcing steel. Remember, concrete is good in compression, but weak in tension, so the reinforcing steel provides the strength in tension and in shear. When designating rebar, size, spacing, and location are the minimum pieces of information that need to be provided. A typical note of rebar on a drawing schedule might look like the following. 2 number 5s at 19 feet long at 2 foot 6 on center. And the place on 1.5 inch chairs simply means how much you need to chair it up off the bottom. Another one would be 8 number 10s by 14 foot 6 at 12 inches on center, and in this particular note, at the top. As discussed earlier, columns are vertical support members designed to carry the loads from floor to floor and then on down to the foundation. They are reinforced and are located on a grid system called column lines. The information about them can typically be found in a column schedule. Columns are typically round or square with an occasional rectangular shape. The reinforcing steel will be banded together with ties as shown here in this diagram. As just mentioned in the training, all columns are located on some kind of grid system with a numbering one way and letters the other. A simple column schedule will identify the intersection of each grid line with the column size, reinforcing steel, and tie size and spacing. Column schedules can get very complicated, which we'll take a look at during the drawing review. Here we have a column getting placed showing the column and footing reinforcing. And here we have a structural flat slab deck getting poured over rebar. And on this structural deck for a parking garage, we see beams spanning from one side to the other, with rebar spanning from beam to beam. This would be a one-way slab. There is also post-tension cables that are out of view in the concrete beams. Okay, back to the gateway tower drawings. Most structural drawings will start off with a general notes page, a page that contains information such as design criteria, concrete notes like PSI of concrete, minimum coverage of rebar, typical joint information, and structural steel framing notes. A lot of information about the specifications can be gathered here. The first plan in a structural set will be the foundation plan. Like floor plans, the foundation plan is showing the layout of the lowest level portion of the structure, usually the same as the lowest level floor of the architecturals. There's a lot of information and section cuts directing the builder to additional information. Note, the column line grid system is the same as the architecturals. Looking a bit closer, this is where you'll find the information about a slab on grade. The note reads, 5-inch thick concrete slab reinforced with number 3s at 12 inches each way over compacted fill. Note the structural plans will follow the same sequence as the architecturals. so the first floor will be the next. Note, they are called forming plans because what we're doing is forming the structural deck, followed by the second floor. Next, the third through the seventh floors. Note, when gathering information about this plan, everything is times 4. 8th and ninth floor forming plan. The 10th floor. The penthouse floor plan. And the penthouse roof plan. In this set of drawings, the engineer has chosen to develop a column schedule based on a column line grid system and a column type. So what is seen on this plan is each type of column has been designated a number. So jumping ahead to sheet S5.2, where the column schedule is located, we see a type of column listed across the top of the schedule, elevations along the left side, and reinforcing requirements as it goes up through the building listed in the schedule. And on the bottom right, we see all the column shapes, reinforcement, and tie configurations. Looking closer, we see the columns start at the foundation, which makes sense, and go to the elevation they top out at. This is a very creative way, both graphically and informationally, to provide the column requirements. In column C1, the vertical reinforcement starts with 8 number 9s, and starting at level 5, they reduce down to number 8s. And here we have an enlarged view of the column shapes, reinforcing, and tie configurations. Schedules can be used for any system, like here for the building pile caps. Followed by several pages of details of columns, walls, and footings and the pile caps. On this page we see interior and exterior column and footing details, also showing the backfill requirements along the wall. Other items that I would like to mention is note how the use of a dashed line to indicate the building wall beyond the column, while the same dashed line is being used to indicate ties around the rebar, while the rebar is shown as a solid line. This multiple use of the same type of line is all part of learning to read drawings and interpret information. Also, we have an auger cast pile that is going down deep into the ground, showing it as it continues using a cylindrical broken line. On this page, more detail is shown for the auger cast pile, showing the rebar, the depth of the rebar, and tie spacing, to mention a few. Note how the break line has been used to illustrate the depth of the pile. Also note an elevator pit is detailed and a retaining wall joints detail. On this sheet, more foundation details and a site detail of a trench at the garage entrance. This usually would be found on civil drawings. This is why I suggest flipping through all the drawings in the beginning and investigating the documents. For fun, let's look closer at this elevator pit. What we see here is as the auger cast pile comes up into it, it's got a 4-inch inset, shows you what the offset of the rebar is, shows you how the rebar ties go up into here, and how the rebar extends up into the wall. We see some embeds for this steel beam, and we see a little bit about how this steel beam is attached to the embed with a field weld. With even a closer look at this steel beam, the part that the concrete contractor would typically be responsible for is the embed, and how the embed is attached with these double-sided bevel welds that are 3/16 inches, 3/16 inches fillet, 1 inch returned top and bottom. This is why we call them details. You get a lot more detail. Note here the auger cast piles, pile caps, and shear walls are all specified in the schedules, and the sections are showing how it all goes together. It is not uncommon to show plan details as shown here for the column pilasters. Let's zoom in and take a closer look at this concrete wall section. Okay, let's start off with the footing. Footing is 1 foot by 2 foot, and it says it has 3 number 5s continuous, which are right here, here, and here. It says it has a number 5 at 12 inches on center that's got a little hook on it, this little U-shaped bar right here. Note, it's got a continuous keyway. It's got a 1/2 inch expansion joint filler before the slab comes into it. And we're coming up the wall. We've got number 4 continuous at 10 inches on center. These are the horizontal bars. And we've got number 5s at 10 inches on center, the vertical bars. And the wall is 10 inches thick. And note, we have a center line indicating where the column line is, and so where the relationship is between the footing and the column line. Also note, we have a slab elevation and also a relationship between the slab elevation and the top of the footing, which is 2 feet. Later in the set, the shear wall schedule will relate back to these plans for additional information for the shear wall rebar. Note how the engineer relates back to the floor plan and elevations with the column line references. As we move on up through the building, we continue to see additional details. The details have phantom architectural delineations on them to better show how the building goes together. On this sheet, we have additional information for the post-tension cables. Post-tension cables are banded wires that adds additional compression to the concrete, allowing thinner sections and a lighter structure. After the concrete is poured, it reaches specified maturity and the cables are tensioned. The details here are showing much about how this system works. On this sheet, we have additional upper level structural details. Note how the designer has chosen to delineate some of the architecture also. Here, we catch up with the shear wall schedule. We saw plan views earlier in the video. Note the extreme amount of information that is included in this schedule. We have been looking at gateway towers and an engineer's particular way of delineating a structure using mostly schedules and details. Here is a different engineer showing rebar layout on the floor plans. Also note the column line layout systems, the north arrow, the scale, and how the revisions are being handled. Okay, let's take a little bit closer look at the plan we were just reviewing. And you can see here that we've got number 4s at 8 inches on center top. Here they're showing number 4s at 12 inches top along here by 8'6" long. They've got a number 5 at 12 inches on center by 8 foot long with a little hook bar. So anyhow, it's an interesting way of trying to delineate the rebar on a plan. And here is another engineer's partial level framing plan where we see both foundations and elevated structures being delineated. Let's zoom in a little bit. And we can see here an interesting way of making section numbers instead of the typical little round circle. They just put an arrow pointing to it. You can see here the foundations, the footings are shown as dashed lines. And over here you can see that there's some kind of a, looks like a wall that's probably fallen right along that area here. And what's going on here are, these are beams and joists running from beam to beam. Also note, there's a sophisticated column line system. So as you can see, the architect and engineers all have a different way of delineating their plans for the contractor to build from. Remember the Lego project? I started with an image. Flipped through all the pages and followed the instructions. And 12 hours later, I had it. I brought the image to life. Okay, this is the end of Unit 6, Structural Drawings. Continue for a few more pages. We will review the final Test Your Knowledge activity. A separate video will review the answers when you are complete. The final Test Your Knowledge is a comprehensive review of the entire Print Reading for Concrete program and structural drawings. So go to Unit 7 in your student handbook and pull out the answer sheets, and we will review what you're going to cover. Page 1. Numbers 1, 2, 3, and 4. Just answer the questions. Page 2, question 5. Identify the following types of lines. Question 6. Identify the marks, numbers on the section cut indicator. Page 3, question 7. Add and subtract the following numbers. Question number 8. Convert the following into decimal equivalences. Question 9. Find the area of the following shapes. And don't forget to show your work. Number 10. Find the length of this line by adding up all the dimensions along the line. Page 6, number 11. Identify the following portions of a foot in 12 inches as indicated on the scales shown below from the 0 mark. Note, the 0 marks are here. Page 7, number 12. Identify the following dimensions shown on the scale by these lines. Page 8, number 13. Measure the following lines using the scales indicated, meaning eighth inch equals a foot, measure this line. Quarter inch equals a foot, measure this line. On down here for 14, mark off the following lines using the scale indicated, meaning I want you to mark off 17 foot 10 using the quarter inch scale for a foot, starting here, going this direction. Page 9, number 15, using an engineer's scale, measure these lines. 1 inch equals 10 foot, 1 inch equals 30 foot. As an example, number 16, mark off 150 foot using 1 inch equals 20 foot. Again, starting here at the arrow and going this direction. Page 10, number 17, find the missing dimensions for this building, and the missing dimensions are identified by these exploded stars. Page 11 and 12, using the gateway tower drawings, answer the following questions. Okay, stop here and do the work. Good luck. We're almost done.